Hello, everyone. For today's Rising Scholar Symposium, I will be presenting my project on analyzing energy efficiency in buildings. Just a quick little introduction. My name is Rohan Dasgupta. I'm a senior at Basis Independent Silicon Valley, and I'm presenting to all of you today from Saratoga, California. My mentor was Ryan Sander, and the reason I picked up this project was because I was interested in the smart building concept and in applying artificial intelligence and machine learning to improve the energy efficiency of buildings. So for some background on this topic, energy efficiency at the moment and for several years has been a crucial global issue. High energy costs in both households and businesses alike have impacted and currently are impacting the global economy. Extreme conditions due to global warming, in particular hotter summers and more frigid winters, have exacerbated the energy crisis, and geopolitical instability is also currently playing a role and has been playing one for quite some time. So what exactly is the smart building concept that I talked about in the previous slide? So smart building refers to a process where the building collects energy consumption data from devices and sensors. The goal is to provide concrete recommendations for enhancing the energy efficiency in different parts of the building. The way I approached this project was I utilized artificial intelligence-based supervised and reinforcement learning to optimize energy consumption. So over here, you can see the sample building data I've provided. This is just a snapshot of a really big file that I used. As you can see, the columns are basically the features that separate the data. You have the building type, the climate zone, the total area, and so forth. And the energy part, the part that's actually relevant to this project, can be represented by the efficiency heating, COP, as you can see over here, the COP efficiency cooling, and the kBTU per square foot, which is represented as British thermal units. So the way I approached my project was through three general steps. So I conducted feature engineering on the data, basically all these features, as you can see over here, the headers. I basically separated the data based on those features and had them all get processed at like the same time. I used that said featured engineer data to train the models, and then I evaluated the trained models onto the test data sets. So before that, I explored previous different energy data sets from different building types in both Kaggle and Keras. So I used both supervised learning tools, Lazy Predict in particular, to evaluate the performance of regression models, and Energy Plus to provide the necessary building features, which overall helped me practice supervised learning, which in other words is differentiating the data based on those features and actively like controlling the environment for the model to make it, the predictions. And then for the reinforcement learning part of the project, I used EnerGym. So reinforcement learning is basically the way I performed all of these repeated trials. Basically, like the model kind of ran several trials, then learned from its errors, and then kept going forth. And the test data set was kept the same throughout for equal comparisons to be made. So some observations I made throughout the project was that pre-processing the data strengthened the model's efficiency. As a result, the model was able to identify different parameters, for example, light efficiency, HVAC outputs, electrical efficiency. In doing so, it determined the energy usage of the building data and the associated relationships, analyzed the data the way I wanted it to, and it filtered out all the non-relevant information to its algorithm, basically all the information that didn't factor into the calculations. And the outcome was that the algorithm strengthened the model's recommendations. And over here, you can see the analysis of the building data taken for 1,000 samples through different regression models. So basically, as I mentioned before, all of these regression models were evaluated on the on different samples of the building data, which you can see again over here just for reference. And it provided all the necessary parameters. It provided the adjusted R squared, the regular R squared, the RMSE, which I'll get to later in a couple of slides, and the time taken to produce said results. And over here, we can see the prediction error results, basically the strength of the regression models overall on the number of samples. So basically, I took it for 100, 1,000, and 10,000 samples and represented a bar chart against the RMSE values, which is basically the root mean squared error. It basically explained the prediction error, the difference between the predicted amal targets and the actual targets that resulted as a result of the regression. And so the conclusion of my project is that the analysis was comprehensive and accounted for all the relevant aspects of the data, qualified different levels of energy efficiency, and it reported the time to produce the results, the R squared values, and the RMSE values for each regression model. And as I mentioned before, I tested it for 100, 1,000, and 10,000 samples. As you can see again over here, if you just need this for reference. So as you can see, the RMSE values decreased from 100 to 1,000 samples, then stagnated afterwards. The overall trend we can see is that increasing the number of samples basically led to a decrease in the prediction error overall. And here are my references, as you can see over here. And thank you for listening. Additionally, you can also refer to my paper over here, where I also had a lot of the same charts. This is slightly larger than the chart I gave for the building energy data. And you can see the output data for 100 samples, 1,000 samples, and 10,000 samples, which again are reflected over here. Thank you for listening.